introduce VCSELs for those of you who are not familiar with it. It's a vertical cavity surface emitting laser. Primarily, the reason why it's very, very exciting is because it has excellent optical coupling, whether it's to free space optics or to optical fiber. Long time ago, we already started to point out the VCSEL's advantage really is in its small volume, so low threshold current and low power consumption, wafer scale testing, and low cost fabrication. And this is particularly in comparison with an edge emitting laser, which requires you to cleave facets and then to do facet treatments. And these so-called assumptions and so on and so forth have been written for about 30 years, or actually longer, 40 years. One of the advantages, it has single longitudinal mode because it's an extremely short cavity. And in addition to that, 2D array fabrication, or naturally formed in 2D array. Of course, in another 1 hour or so, 2 hours, the plenary talk given by Professor Kenichi Iga will cover a lot of the VCSEL development. Professor Iga, of course, proposed surface emitting laser in 1977. But it took a long time before it became a reality. But today, the vast majority of applications, including fiber communications, primarily multimode fibers in data centers, printing, and what's extremely exciting, I would say today, is 3D sensing, the facial recognition, and optical coherent tomography. Both of these applications were made only possible with VCSELs, with its array format for the former, for the array, for the 3D sensing, but with single longitudinal mode, widely tunable structure for the second, optical coherent tomography. Both of them brought you forward the third dimension in a camera, or fourth dimension, if you will. It will, in time, 3D video. So it's exceedingly exciting. Now, the brave new world, of course, is to go towards LiDAR or driver assistance. I think last year's plenary talk of our Opto conference, there was a LiDAR talk. It's still a topic that's exceedingly exciting. And I believe in Tokyo this year, later in the Olympics Games, we are going to see many, many more of these cars with LiDAR in reality. So it's an exciting new world. Of course, next door in the Moscone West, you have all the AR, VR shows. So this is an exciting time for optics, exciting new dawn, if you will, for all the 4D, 3D, and so on. And this is just a market survey, just to indicate chips alone can go to $1 billion market. And that's not even adding on systems. Usually you multiply by a factor of 100. So with all of this, it is a really fantastic beginning. It's worthwhile to just go back a little bit. I'm sure, again, if you go to the plenary talk, you'll hear more about this. Professor Ken Iga's work, pioneering work, a first demonstration of CW operation of VCSEL. At that time, the mirrors were gallium arsenide, L-gas, DBR on one side, but silicon dioxide, titanium oxide, dielectric mirror on the other side. And soon afterwards, Bell Labs and Bellcore, a team of collaborators, demonstrated these lasers. It's a really shocking picture, actually. Very, very densely populated 1 micron, 2 micron diameter posts. And that time already could work room temperature CW operation. However, these lasers were not planar or not addressable, so making it very difficult to actually test them or use them. So our team at Bellcore first started exploring the use of proton implantation to provide current confinement. Proton implant semiconductor lasers, of course, in the 70s were already introduced first by Bell Labs and then Xerox PARC and so on, but for edge emitting lasers. For VCSEL, it's slightly different because you need to go deeper. To realize that you could actually use proton implant to provide to resulting CW operated lasers and directly modulated lasers was non-trivial, but nevertheless, we did that in 1990. And soon afterwards, independently addressable array, and this was work by Anne von Lehman, one of my colleagues at Belcore, demonstrating 8x8 independently addressable array. And then soon afterwards, we also demonstrated 32x32 matrix addressable array, all in about 1991, 1992 timeframe. And it is really fantastic to see that these lasers, after 30 years, finally coming to fruition. Soon I will discuss, and I'm sure matrix addressable array and independently addressable array will also come to light. Another work that we have done in my group was to realize that 940 nanometer was actually a very interesting wavelength, simply because it had water absorption in the air. So providing possibility of better signal to noise ratio or prevention of your detector from detecting more stray light, in other words. So in 1998, we published a 1,000 element laser array emitting at 940 nanometer. At that time, CW operation 2 watt and pulse operation 5 watt. We thought that was quite a hero work. Indeed, at the time, the power was really fantastic. All the lasers were actually single lobed and single mode with 8.8 degrees full width half maximum and can be focused down to 0.8 micron and 400 micron, 0.8 degrees and 400 micron spot. And so therefore possible for pumping of solid state laser. The unfortunate thing is that at the time, there were not as much interest in lots of the applications. So we didn't really pursue too far. We did go through some time of flight 3D imaging application though, but nevertheless, it was a bit early for the time. And then, of course, today, the most exciting part about VCSEL is the application in 3D sensing, brought forward by Apple in the iPhone 10 first, using it to using lots of dots to derive the deflection of individual points. So how it works is the following. They use a roughly 300 element laser array and split the 300 dots into 30,000 dots, and using a diffractive optical elements as such. And the wavelength of choice, lo and behold, is indeed 940 nanometer. Not really anybody's standard, so to say, but it's possible to detect with reasonable detectivity with CMOS camera, and also improved signal to noise ratio, as I mentioned, because of stray light is absorbed by water vapor in the air. And so how it works is that if you have a set of predetermined pattern and shine onto a surface with depth information, the line will be altered. And you can calculate the deviation, and from that, getting the entire depth map. And it's really shocking, actually, in a sense, to see that 300 lasers in a chip can be brought forth into a commercial electronics components and device. And so these things, I don't know whether it's still current generation. I must apologize. This is all what I can dig out from the website, right? So the website gives you certain images, and I don't know whether it's state of the art, but nevertheless, it's interesting to look at. And these lasers inside going through certain guidance lens and so on, and then diffractive objects. And what it does, the DOE does, is to spread out, to replicate each of these images of the laser array into, say, 100 times or 99 times. Interesting. And then lots of these dots, and the dots on your face is then calculated back to find the depth. One thing that is quite interesting is that in water, because of these patterns are all random and they are replicated, and to find the origin, if you will, to find the 0 point, and if the face is tilted and so on and so forth, and yet still being able to recognize you, that obviously requires lots of computation. And part of it is about finding a unique pattern that's designated as ground zero, so to say. And so therefore, the pixel usage, whether each individual laser is considered a pixel resolution or not, is part of this calculation. And in essence, it's interesting to find that maybe you're trading off by gaining the depth resolution, you're trading off the pixel resolution. And that gives us, I guess, more motivation to study and to understand and to build more lasers. But nevertheless, VCSELs really, the array really coming of age. For the longest time, people ask me and ask many of us, why do you make arrays? We say it's natural to make arrays. Why not? But there's no reason per se, no applications all this time. And so it's just for fun, we make arrays. But now there's a real application, and real applications in everybody's hand. So this makes it exceedingly exciting. Okay, so let me move on to tell you what high contrast grating may have something to do with this extremely exciting VCSEL world. Well, one part of the VCSEL challenge had always been the growth of these layers, that you have to grow them extremely precisely with precise composition. And so you make DBR mirrors in the bottom, n-doped, and then quantum well, and then top DBR mirrors on the top, p-doped. And the invention of the oxide confined VCSEL obviously made it possible to make low voltage and high wall plug efficiency. And indeed, it's the prevalent structure. Today's actually, most of the VCSEL are combined with the oxide confined structure as well as proton implant for high speed. So the thick DBR really requires high precision growth. It gives you a very long epitaxy time, lacking of polarization control because it's planar. And then the array density is quite limited. I just now mentioned you want larger arrays and many, many more elements. But nevertheless, because of the DBR being so thick, you need to etch down and to etch a deep hole to allow oxidation. That resulted in the possible lacking of capability of making it really highly dense, densely packed. So one of the DBRs for 940 nanometers is probably about 5 or 6 microns already. And for 1550, very often it's about 12 microns. It's really very thick. And the reason why it's really thick is because delta N is very small. And you need to use these high, low index materials, all lattice matched compound semiconductor to obtain coherent reflection. And so therefore you have high enough reflection, certainly for the bottom mirror. So the thick DBR presents a problem, and this problem came from the fact reflection is in the direction of periodicity. I think many of you probably seen this slide before, but I apologize for the repeat. But nevertheless, I still find this slide the most revealing part, which is asking the question, can the periodicity be orthogonal to the propagation? And certainly you can, because in microwave and radio wave regime, we do that all the time. We use metal. And this metal is orthogonal to the propagation as long as the period is, or the feature, if you will, is smaller than the plane wavelength. And you create a K vector in the plane of the propagation, orthogonal to the propagation. Then we create a K vector alteration, and which resulting kz square less than 0, meaning that every light needs to be cannot propagate, must reflect. And microwave oven is the best example. The door of the microwave oven is full of holes, single layer, very light reflector. But of course, metal has absorption, and it cannot work so well for VCSEL. Maybe it can work for other applications, but not so much for VCSEL, because VCSEL requires very, very high reflection. So we've started to look for this solution. And the first time we did was really just looking at a grating, silicon on silicon dioxide. By simulation, we found a broadband reflector. Actually, the first author is sitting here after some 20 years, returning to the field. Anyway, so the reflection is broad, but unexplained. It wasn't until much later we actually realized that it can be actually theoretically explained simply by looking at modes propagating in the bars. I know that now today there are so many different theories and different simulation packages. And so indeed, it's all EM waves. And so it all works. Whatever works and not resulting in garbage in, garbage out simulation, it's fine. But I must say that in 2004, it wasn't so that much readily available. So we had to struggle a lot. And what we found is that in the wavelengths normalized by period, within between 1 and refractive index of that material, there exists a regime where you can get broadband reflection, or you can get a whole bunch of garbage resonance lines that cannot be explained. And later on, in one of our papers, one of my former students indeed was able to explain that. And indeed, its surface normal reflection, turns out thickness and index contrast do play a role. This index contrast may not require as large as we initially thought it needed. We use 3.5 to 1, like the extreme case. But I believe many of the papers in the session and other people publish even something like about 1.9 to 1.5, that type of ratio can result in a very good result. Anyway, our first effort was to demonstrate this onto VCSEL. I always want to give credit to my former student, Mike Huang. When he worked on the high contrast grating with simulation, that time the simulation tools were not so good, at least not available in my group, not good at all. And it really took him a leap of faith to believe that this holy bar structure can actually replace VCSEL. Initially, obviously, we fabricated, didn't work, right? When it didn't work, you question whether it's the theory that it didn't work. But he believed in it, and he found the reason why his processing was no good. And so he demonstrated the first this VCSEL. And the high contrast grating was selectively etched. It was a gallium L-gas material using e-beam lithography fabricated grating, and then a selective etching to remove the the underneath layer. So it's a floating MEMS or floating structure. So first thing we did was to find out whether it indeed, like everybody expected, has the polarization determination factor. And indeed, using e-beam, we can write gratings in all angles. And we can see that there's at least 20 dB and above a Simon suppression ratio, so you can control the grating dimension. So soon afterwards, we demonstrated 850 nanometer, 1550, 1060, and 940 nanometer. All wavelength works. And finally, we also flip chip bonded onto silicon using a silicon high contrast grating as a grating for 1.55 micron VCSEL. So all of these do work. However, all of these cases have MEMS or have the HCG floating. And we wanted to make it as a MEMS structure for tuning purpose, but nevertheless, this structure does not facilitate array fabrication. So recently, one of my students demonstrated this using oxide underneath the grating, which is actually aluminum gallium arsenide, and oxidized as aluminum oxide, so that the grating sits on top of a wet thermal oxide, same material that you use for the oxide confinement structure. So with this structure, it is now monolithic and it's very thin from the active region, and it facilitates the fabrication of an array. So we demonstrated recently this array. The power, we at least obtained 7 milliwatts, but they can still go on this room temperature CW operation. 2 volts at turn on voltage. We believe it should be even better. This is a 940 nanometer VCSEL. For those of you who are familiar with these numbers, this is actually not a bad number altogether. And it facilitates a very highly dense packed VCSEL array. And so this is something that we are continuously working hard on. Next one is about tunable VCSEL. As I mentioned to you that it's naturally single longitudinal mode, so it's naturally possible to, if you can change you can tune the cavity length, you can continuously sweep the wavelength. This is so important for an application that is the optical coherent tomography application. Without continuous tuning, you wouldn't be able to get a very real-time high resolution signal. So we have started doing this MEMS tunable VCSEL since 1994. However, because the DBR was thick, so the tuning range and tuning speed was rather small. Let me just jump ahead. I know my time is limited. I want to say that the 1550 nanometer tunable laser right now is commercialized by bandwidth 10 with 10 gigabit, but I think they have actually better data right now with reliability data as well as a wide tuning range for 1.06 micron OCT applications. I think on Wednesday or Thursday's VCSEL session. So I want to just say a few words about tunable laser. So tunable laser, I should say that at 1.06 micron, about a couple of years ago, we demonstrated 40 nanometer tuning. Everybody who had seen this slide often asked me, gee, I think you didn't really improve very much, huh? Since 1994, 1995, from a 34 nanometer to 40 nanometer. So we said, well, that's really true. And part of the reason is that we had always designed this air gap to be in resonance with the cavity. And so if you come in from cavity, high index, low index, high index, and the air gap is low index, it's all in resonance. So as a result, the tuning range has a staircase that looks like this. And this is a long story, but I invite you to read the paper. By designing the cavity off resonance, we are able to obtain a factor of 2 improvement in tuning. And indeed, this is our recent result of 73 nanometer. As I mentioned, I think BEMA 10 tomorrow will be presenting actually even wider tuning range, continuously swept range. Again, because of high contrast grating, you can actually get broadband as well as very, very fast tuning range, fast tuning speed. And finally, I just want to say that high contrast grating, we have been doing 1D grating, but even 1D grating can result in broadband reflection, air coating, or high Q cavity. But the rest of this conference, of course, are going to be extremely exciting with all the possible 2D structures. And whether you call it metasurface or metastructure of photonic crystal, I think it's all an extremely exciting manipulation of light with dielectric material or semiconductors. So I think because I delayed your beginning with the computer issues, so I will not say too much more about the rest of other applications, but just again, welcome you to the conference and hope you stay for all the invited talks and contributed talks. Certainly, they are very, very exciting. And thank you very much for your attention.